Form 4 Physics Chapter 13 Sound Waves. This is the term contained and specification points from 3.23 to 3.29. You can refer to this chapter in Physics Pearson Edexcel International book from page number 123 to 129. Today we will be learning about the sound waves, the type of the sound wave, the audible range that a normal human being would have, and we will be learning about some practicals to investigate the speed of sound in air and to investigate the frequency of sound wave using an oscilloscope. And along with that one, we will be learning how a microphone can be used to display a sound wave in an oscilloscope. And we will also be understanding about the pitch of the sound and how it relates to the frequency, and loudness of a sound and how it relates to the amplitude. Okay, so to start with, what type of wave the sound goes to? Sound waves can be categorized as longitudinal waves. That is because when sound transfers from a particular medium, the molecules in that medium vibrates parallel to the direction of the sound wave. So it causes compressions and rarefactions. So these are known as compressions and these are known as rarefactions. All those molecules that we were talking about shows this pattern. While vibrating back and forth along the direction of the wave, the sound would transfer its energy from one point to another point. Then, reflection of sound. Sound waves, as all the other waves, can be reflected. Not only that, it also can be refracted. When sound waves reflect, it obeys the basic rule. Incident angle would be equal to reflected angle. Not only that, if a sound wave goes and strikes an object, that sound wave would reflect back. This phenomenon we call the echo sounding. You might hear this echo when you clap in front of a series of mountains in front of you. You will hear that clap back. So this is actually a useful theory that we need to know. Why it is useful is we can use it to determine the distance to the barriers. So how can we find the distance to the barriers is, we can find the speed, actually we know the speed of sound that it transfers through a particular medium, through the data that we can obtain from internet. Then when we create a particular sound, that sound will transmit and it will meet the object, then it will reflect back to the receiver. So the distance that the sound has travelled is actually twice the distance from the point where the sound is created to the object. If we can measure the time taken for the sound to transmit and reflect back, which is t, we can use the general equation, that is speed equal distance divided by time. From there we can subject distance. So distance will be equal to speed into time. But in here we do a special thing. We divide it by 2. We divide it by 2, that is because it's actually twice the distance between the source and the object. Right. Refraction. Under refraction, what happens to a sound wave is when it passes from one medium to another medium, the waves, if they slow down, it will bunch together, causing wavelength to reduce, and the wave will bend towards normal. If the waves speed up, then wavelength will increase, the waves will bend away from the normal. That is also as usual, as same as all the other types of waves. Then, the audible range. The pitch or the frequency that a normal person would hear, it is known as the audible range, which can be categorized from 20 Hz to 20,000 Hz. Any sound wave below 20 Hz we call it infrasound. Any sound wave over 20,000 Hz we call it ultrasound. Okay, so we hear 20 Hz to 20,000 Hz, that is usual human range. Infrasound below 20 Hz, you can see that wavelength is greater, and ultrasound, which is greater than 20,000 Hz, you can see that the frequency gets very high. So, for an example, now what you will be hearing is a sound that you would observe starting from low pitch or low frequency to high pitch. So what you observe there is, it started from low pitch, which is known as low frequency, and it ended from high pitch, which is known as high frequency. That is the relationship between pitch and frequency. Now, we move on to an experiment. How to determine the speed of sound in air? It's very simple. Call for a friend. Then, with the help of that friend, you ask your friend to go like 100 meters away. How would you measure 100 meters? You can use a click wheel where it clicks every 1 meter. So when you make that, but however it should be a straight line distance. When you make that straight line distance of 100 meters between you and your friend, then take a piece of wood and clap it with another piece of wood above your head. Why above your head? Because the other person who is 100 meters apart have to see you. So as soon as the second person sees you banging the two woods, he has to start the stopwatch, and as soon as he hears the banging, then he has to stop the stopwatch. So what he would measure is the time taken for the sound wave to travel from you to him. Okay, so we know the distance 100 meters. Your friend measures the time. We can repeat it several times. This allows us to identify anomalous results, and it allows us to increase the precision of our measurements. Reliability is very high when we do this repeating and averaging. So we can use the equation speed equal distance divided by time to measure the speed of sound in air. Very simple experiment. Okay. Now we'll discuss how we can use an oscilloscope to display a sound wave produced by a microphone. It's very simple. We connect the microphone to the oscilloscope, and the oscilloscope screen would show us the wave pattern. In here, the x-axis, the horizontal axis, is time-based. So we can change the settings so that we can change one square would show what relevant time. For example, we can say one square would show 1 second, one square would show 1 microsecond, likewise. According to that one, we can approach for calculations. So what you have to remember is x-axis is time-based. Now this is an example of what we have just discussed. Now suppose that this is the wave that you have seen in the oscilloscope screen. And the time-based x-axis, let's suppose that I have set it into 0.1 second, which means horizontally 5 squares would show us 0.1 second. Now we'll see for one complete wave how many squares have occurred. 1, 2, 3, 4. It tells us that the time taken to complete one complete wave is 0.1 times 4 squares, that is 0.4 seconds. So just now we found the time taken for one complete wave. How can we find the frequency? We have to use the equation. Frequency equals 1 over time period. So that is 1 over 1 0.4, 2.5 hertz. That is how we refer to an oscilloscope screen and determine the frequency of sound wave. We measure the time period, time taken for one complete wave with the aid of the grid, and we use frequency equals 1 more time period. Okay, then the loudness and the amplitude. When it comes to a sound wave, the loudness, or in words that you can understand, the volume, is represented by the amplitude. So if the volume is low, that means quiet sound, amplitude is low. Amplitude is, you know what is the meaning of the amplitude. That is the maximum displacement a wave can make from its resting point. So in this red wave, you can see that the maximum displacement it made from the resting position is very low, but in blue wave, the amplitude is very high. So we can categorize these two waves. This is the quiet wave and this is the loud wave. Or in other words, we can say low volume, high volume. Or in other words, we can say low amplitude, high amplitude. That is how we can categorize sound. Okay, so that's the end of the story about sounds. Now if you refer to page 129, you will see some questions and do them in another separate book. We will discuss them once the school starts.